When most people hear the word geological hazard, they picture a single dramatic event, a big earthquake, a volcano erupting on the news. But as a disaster management professional, you know the reality is more complex. Geological hazards are a family of processes often linked together in dangerous chains. Shaking triggers landslides, landslides cut roads, block rivers, create floods, ash from a distant volcano grounds plains and disrupts health systems thousands of kilometers away. In this session, we'll walk through three major groups of geological hazards: earth movement, mass movement, and volcanic hazards. As you listen, think not just about the science, but about the operational question behind each one. What does this mean for exposure, vulnerability, and our capacity to respond? Earth movement, when the ground itself shifts. Let's start with Earth movement. Hazards driven mainly by the movement of tectonic plates and faults in the Earth's crust. First and foremost, earthquakes. An earthquake is a sudden release of energy along a fault line that sends seismic waves through the ground. For communities, that means intense shaking that can bring down buildings, bridges, and critical infrastructure in just a matter of seconds. The key point for professionals: people are not killed by the magnitude number on a seismograph. They are killed by collapsing structures, failing non structural elements, fires, and cascading failures that follow. After the main shock, the story doesn't end. We face aftershocks, smaller quakes that follow the main event, sometimes for days, weeks, or even months. These can be deadly because they hit already weakened buildings and infrastructure. From a risk management perspective, aftershocks are a test of decision making under pressure. Do you re enter buildings too early? Do you allow partial operations in hospitals, schools, and offices that are structurally compromised? A good emergency plan treats aftershocks as a part of the hazard, not an afterthought. Another piece of the puzzle is surface faulting. In some earthquakes, the fault actually breaks the ground surface. You might see the land offset by a few centimeters or several meters. That matters because any structure, pipeline, or road directly crossing a fault trace is at extreme risk of permanent displacement or just shaking. For planners, this is why fault avoidance zones and microzoning regulations exist. You simply don't want critical facilities straddling an active fault. Then we have soil liquefaction, one of the least visible but most damaging effects in certain conditions. In loose, water-saturated soils and strong shaking can cause the ground to temporarily behave like a liquid. Buildings tilt or sink, buried pipes float to the surface, and port areas can become unusable. From a business and infrastructure standpoint, liquefaction can quietly multiply losses. The building might survive structurally, but the foundation fails, utilities are destroyed, and operations are paralyzed. For you as a professional, this is a reminder that hazard maps must go beyond where shaking is strong to include where the ground will behave badly under that shaking. Then we come to mass movement, when gravity takes over. Earth movement frequently sets the stage for our second category, mass movement hazards. Here, gravity is the driving force, pulling rock, soil, and debris downhill. The most well-known are landslides. A landslide is a downslope movement of soil or rock, often triggered by heavy rainfall, earthquakes, or human activity like deforestation and road cutting. For communities in hilly or mountainous regions, landslides can bury homes, cut off villages, and block rivers, creating secondary flood risks. From a risk perspective, even a small, localized landslide can have outsized impact if it blocks only access roads to a hospital, a dam, or a key industrial facility. Related to landslides are rockfalls. These are sudden, often fast movements of individual rocks or clusters of rocks detaching from steep slopes or cliffs. These may look less dramatic than a massive landslide, but a single boulder can destroy a house, a vehicle, or a section of road. For road authorities and transport planners, rockfall risk is a daily operational issue, especially in mountain corridors where a short blockage can disrupt national supply chains. In some events, the material that moves downhill is not just rock and soil, but a saturated flowing mass. That is where mudslides and debris flows come in. Mudslides are flows of fine, water-rich material. Debris flows are even more dangerous slurries of water, soil, rock, and sometimes logs moving at high speed in channels. They can travel kilometers down valley bottoms, sweeping away homes, roads, and bridges in their path. One important operational lesson here is communities that feel safe because they are not directly on a steep slope may still be highly exposed if they are located in valley flows or along channels where debris flows travel. Then there are the slower, often less visible hazards, subsidence and sinkholes. Subsidence is the gradual sinking of the ground. It can be caused by groundwater extraction, mining, natural compaction of sediments, or the collapse of underground cavities. It rarely makes headlines in the way earthquakes do, but it can cause long-term damage to buildings, roads, and buried infrastructure, and it worsens flood risk by lowering the land relative to sea level or river level. Sinkholes, on the other hand, are more sudden, localized collapses of the ground surface into underground voids. They are particularly common in karst areas with limestone, where water dissolves the rock and creates hidden cavities. From a planning and insurance perspective, sinkholes are a reminder that geological hazards are not only about dramatic regional events. They can be highly localized, yet devastating for the people and assets directly above. Then we move on to the volcanic hazards, more than just eruptions. Our third group of geological hazards revolves around volcanoes. Again, the public image is a single eruption, a plume of fire and ash. In a professional practice, volcanic risk is a package of interacting hazards that can persist for weeks, months, or even years. At the center is the volcanic eruption itself, an episode where magma, gas, and ash are expelled from a volcano. Eruptions can be explosive, sending ash high into the atmosphere, or effusive, slowly releasing lava. The style of eruption shapes which hazards dominate and what actions you need to prioritize. One of the most widespread volcanic hazards is ashfall. Fine volcanic ash can travel hundreds or even thousands of kilometers depending on wind patterns. It may not look terrifying, but ash is abrasive, conductive when wet, and very harmful to engines and lungs. It can collapse roofs when it accumulates, contaminate water supplies, and shut down airports and power lines. For critical infrastructure managers, ashfall means air filters clogging, transformers shorting, and visibility dropping, issues that demand very practical preparedness measures like stocking masks, cleaning equipment, and structural checks. The most lethal volcanic hazard is often pyroclastic flows. These are fast moving avalanches of hot gas, ash, and rock fragments that race down volcanic slopes at speeds that can exceed 100 kilometers per hour, with temperatures high enough to incinerate almost everything in their path. From a life safety perspective, there is no realistic way to outrun a pyroclastic flow. The only real protection is effective monitoring, exclusion zones, and timely evacuation before an eruption transitions into this phase. Lava flows are another visible hazard. They are usually slower and more predictable than pyroclastic flows, but they can still destroy everything they cover: homes, roads, agricultural land, and industrial facilities. For planners, the key question is which areas lie in known lava paths and what critical infrastructure corridors cross those paths. In many volcanic regions, land use planning and strict zoning are the main tools to keep people and high value assets away from likely lava channels. Volcanoes also emit gases, including water vapor, carbon dioxide, sulfur dioxide, and other compounds. Volcanic gas emissions can cause acute respiratory problems, acid rain that damages crops and water bodies, and local accumulation of heavier than air gases like carbon dioxide that can asphyxiate people and animals in low lying areas. For health authorities and environmental agencies, gas monitoring is an essential part of volcanic risk management, not an optional extra. Finally, we have lahars, volcanic mud flows that combine water with ash, rock, and debris. They can be triggered during an eruption by melting snow and ice, or long after when heavy rain remobilizes ash deposits on the slopes. Lahars behave like fast, dense rivers of concrete. They follow valleys and river channels, destroying bridges, houses, and farmland downstream. A critical insight for disaster managers is that communities far from the crater but along river valleys can be extremely vulnerable to lahars even when they feel far from the volcano. So, why does this taxonomy matters for you? So why spend time separating earth movement, mass movement, and volcanic hazards into these detailed categories? Because each one interacts differently with vulnerability, exposure, and capacity. Earthquakes and aftershocks test your building codes, your enforcement, and the robustness of your emergency operations centers. Mass movements expose weaknesses in land use planning, road design, deforestation, and informal slope settlements. Volcanic hazards challenge your monitoring systems, your evacuation planning, your communication with aviation and health sectors, and your ability to manage long duration multi sector disruptions. When you profile geological hazards in your area, you're not just drawing lines on a map. You're making choices about who and what is considered safely outside a hazard zone, which sectors must prepare for which type of impact, and which scarce resources for mitigation and preparedness will go first. And as you move forward in this course, keep this mental checklist for geological hazards. What type of geological hazard am I dealing with? Earth movement, mass movement, or volcanic? How can it cascade into other hazards or system failures? Blocked roads, dam failure, power outages, health crises, and most importantly, given limited resources, which combination of hazard, exposure, and vulnerability create the highest risk and therefore demand the strongest action? If you design your risk assessments and plans with those questions in mind, geological hazards stop being a list of scary terms and become something far more powerful, a structured way to anticipate, prevent, and manage real world consequences for the people and systems you're responsible for.